If you're gonna give an introduction to me, or will I just start?
Just please go ahead and start.
Okay. Are we ready? Okay, I suppose it's the top of the hour. So yeah, let's start. So um, my name is Jeff Greenblatt. I am the Vice President of Science and Research at Orbital Assembly, which is a space startup aiming to build space stations in low Earth orbit and beyond. And I'm going to be talking to all of you today about some work that I've been doing, kind of a passion project over the last few years on how we will live in space, um, and really focused on fundamental limitations as well as a number of practical considerations regarding large-scale space settlements. And I will explain what I mean by that and what the kind of constraints are that I'm thinking about shortly. It will mostly be a technical talk, but there are a lot of non-technical implications of it, and I think everybody will find it thought-provoking. So I like to start with this quote from one of the founders of modern exploration and rocket technology in particular, Konstantin Tsiolkovsky, who was a Russian scientist who lived more than a century ago. And basically the idea that, we were born on Earth. All life that we know started on Earth, but if we are a growing organism, perhaps we don't stay on the planet long term. There's a lot of room out there to explore, and as I hope I'll be able to convince you, there are good reasons why we want to venture out into the cosmos. People hear me okay? Just when I do a sound check.
I can hear you okay.
Okay, thank you for the feedback. Just double checking since it's a quiet audience and I can't see anybody. So why live in space? Well, there are sort of any number of reasons. I've listed the ones that I think are the most important here. Maybe starting with the idea that there is room to flourish. Our Earth is getting very crowded, both in terms of where humans live, as well as the land that we are trying to share with the other millions of species that live on this planet. And as I'll hopefully convince you shortly, there's a lot more room in space for humans and as well as non-human species to live and grow. There's also a huge economic factor to going into space if we can start to harness some of the resources, which are quite vast compared to what we have on Earth, although they're currently quite expensive to get to. It also opens up new social and political possibilities because we're not confined by the traditional country boundaries. We essentially have new land that we can create and govern as we wish. And a lot of people are excited about social experiments that you can do in these new communities. There's a sense of exploration and adventure, new technologies that are developed, as well as helping to curb the depletion of resources on Earth by sort of shifting economic activity into space. And while that's a longer term play, it's certainly a convincing argument if the bulk of human activity starts to take place off the planet. And finally, it can be seen in many ways as an insurance policy. There are a lot of things that can happen on Earth if we're contained there that could be existential risks. And by spreading humanity out into the solar system and perhaps one day beyond, we reduce the risk of losing everything by being confined to one point in space, and maybe other reasons as well. So back to the question I started with, what is required to sustain life in space? I see this as, and there's any number of things that you can list, but I see this as kind of boiling down to four main factors, and then I'll talk about some ancillary things and constraints on this. And when I say sustain life, I don't mean just for a few days or months or even years for a small number of people, but I really mean sustainable living in space, building a civilization off the planet. What is required to do that successfully? And so first and foremost, I think, is the need for gravity. We have found over the last several decades, and particularly over the last 20 plus years living on the ISS, that although we're able to make some accommodations for the deleterious effects of microgravity, it is a health hazard, and not all the effects can be overcome with the various countermeasures that we have astronauts conduct, which are honestly very time consuming and limiting. Um, we, all species on Earth, were evolved in a 1G environment. And we know that gravity, that we don't have these problems on the surface of the Earth, muscle and bone loss, changes in circulation, changes in, DNA expression, changes in the shape of the eyeball that sometimes don't go back when astronauts return, and so on and so forth. And so being able to provide at least some gravity, probably or possibly Earth level gravity in orbit, would be a really great way to avoid these problems. And while there's many advantages of weightlessness, particularly for manufacturing and science, we also know how to do a lot of things in 1G. And, for the health of human occupants, it might be good to at least have regions in space where you can produce this artificial gravity, particularly for things like childhood development, gestation. But a lot more research is required. But so I'm going with the first premise that some level of gravity is almost certainly going to be required for a sustainable space civilization. The second is shielding. And by shielding, I'm actually talking about two different but related kinds. One is shielding just from the vacuum of space, of course, and the high energy particles in terms of micrometeorites and other debris that are flying around at high velocity that could easily kill a human if not protected, and can puncture the hull of a ship even with a fair amount of shielding. And so really, adequate shielding is needed for that. But we pretty much know how to do that and reduce that risk to a fairly low level with fairly thin levels of essentially Kevlar shielding that stop the impacts of high velocity particles. The more concerning thing is radiation in space, which is much, much higher than on the ground. And although our magnetic field and the bulk of the planet orbiting nearby blocks most of the radiation, there's still a fair amount that gets through in space. And in deep space, the radiation is at the full level. And we really need very thick shielding in order to protect humans and other organisms from DNA damage and other pretty serious conditions. It's been estimated that if you're just using kind of dumb mass, you need about 10,000 kilograms or 20,000 pounds for every square meter of exposed area of the outside of the spacecraft. Depending on your assumptions and exactly what material you use, you might be able to reduce that a little bit. There's also the idea of using what's called active shielding, which is using electromagnetic fields to sort of deflect high energy charged particles. But one way or the other, there's going to be a fair amount of mass and energy used to provide a shielded environment for humans to live and thrive. So that's the second requirement. Then the third one is sunlight. The most abundant source of energy in the solar system is the sun. Despite the small amounts of other, energy sources that are going to be present, some nuclear materials, say on the surface of the moon or in asteroids, the gas giants. But by and large, the future is going to be solar powered in space. And we not only need sunlight for electricity, but we also need it to provide heat and particularly light. If we're eventually going to be growing all of our food in space, we need abundant sunlight to be able to provide that agricultural productivity resource. And we also are probably going to have some Earth ecosystems that we build artificially in space, even if it's just a small central park, or it's a forested area or a nature preserve where we have endangered species that are living alongside us that people can occasionally visit. We're going to need a lot of sunlight in order to provide growth energy for all of those plants to thrive. And so on Earth, the average person requires about several thousand square meters of land area just to grow their food, and a like amount for the ecosystems that exist on this planet. I'll get into the land area per person in a moment, but it's basically photosynthesis, and it is the major energy source that we take for granted right now. Our electricity needs kind of pale in comparison to that. So going to need abundant sunlight in space. And then the fourth and equally important one is land. People living in space are going to need more than just a small box to float around, and we're going to need an ample amount of land. Even if it is sort of high density urban living, there's still a lot of land that is required per person, both to live as well as to conduct commerce, manufacturing, moving around on streets and so on, and recreation. We might even want some open area of water so that people can enjoy some semblance of what it's like on Earth with an expansive horizon. On the Earth today, even with 8 billion people, there's about 20,000 square meters of land, or about 5 acres per person alive on this planet, plus roughly 3 times that, 2 or 3 times that in terms of ocean area, because 2/3 of our planet is covered with ocean. Most of this land area is still wild, about 50%, although that number unfortunately does decrease every year. And most of what we are using is for agriculture, forestry, and mining, and very little is actually urban. So while we could get away with a fairly small footprint for urban, we're probably going to need more land for these other uses. We can grow food much more efficiently on the land we have, so we don't need 7,000 square meters. We could probably do it with a couple hundred square meters, or maybe even less. But when you kind of consider all the needs of a civilization, we're probably ending up somewhere in the realm of a few thousand square meters, with roughly a couple of acres of land per person in a space civilization. And that is a very different situation than what we've imagined so far for space habitats. This number is a very rough figure, and it will depend a lot on the economics as well as on what people want. You can have 1 million square meters per person, which essentially means everybody has a private estate. If we're all fabulously wealthy and we want to have grounds to hunt quail or just walk around in a forest, maybe we can do that one day. On the other hand, if we don't have that much, maybe we could get by with just 100 or so square meters, but that's still a lot larger than what astronauts experience today. So land is the other big differentiator. So those are kind of the top 4. And now I'm going to talk about some constraints that will limit sort of the kinds of things that we can do. But as you will see, there's still a really wide open possibilities out there. The first is the question of where we're going to live. There's been an ongoing debate for several decades about where would be best in the solar system for large-scale settlements. One argument is that it should be nearby hard surfaces like the moon, Mars, even fairly large asteroids. They provide a lot of surface area. They have resources readily available. But if you add up all the solid surfaces in the entire solar system, it's a little bit more than twice Earth's area, total area, including oceans. 50% of that is provided by the planet Venus, which is not very hospitable at all, but it does have a solid surface similar in area to Earth's. And none of these locations, including Mars and others, have conditions that are hospitable to living without a lot of technology. And on top of that, the gravity level is nowhere close to what we have on Earth. So for many reasons, none of these are suitable for large-scale habitation, and it is limited ultimately to sort of, roughly twice Earth's area, even if we could use all of it. So the alternative is what has been variously called Freespace habitats, or O'Neill cylinders, pioneered by Gerard O'Neill, who was a proponent of this idea in the 1970s. It was actually first identified in the literature by Tsiolkovsky back in the turn of the 20th century. A brilliant scientist, really, for coming up with this idea. But the idea is that you have an enclosed pressurized habitat, so essentially a big tuna can. It could be several hundred meters or even several kilometers on a side, but it is basically an enclosed pressurized habitat, and it spins fast enough so that you can have Earth-like gravity walking around on the inside of that surface. And you can have several levels within this as well. You can see this illustration by my friend and colleague Brian Versteeg of sort of a modest size habitat that might have room for a couple thousand people. You can see the different levels lit up inside, and it basically offers everything that we need to live comfortably and sustainably. It has Earth normal gravity, protection from space radiation, a breathable, comfortable climate, unlimited sunlight from the solar panels or from large mirrors that can bring light in, and lots of interior space. Another bonus is that because it's floating in space, presumably near the top of one of the large planetary gravity wells like the Earth, it wouldn't be orbiting in low Earth orbit, but it would be orbiting further up, kind of near the moon or somewhere like that. Moving around in space from one habitat to another is a very low energy endeavor, because you don't have to get out of any deep gravity well, and moving from the Earth vicinity to say Mars vicinity or the asteroids, again, it's a fairly low energy maneuver, even though it does take some time. And so there's a big energy advantage of this compared to living on planetary surfaces. So that's the premise that I've gone with. There are those who prefer surface habitats, and they're fine. They can build those too, but there's going to be a lot more room available to build these free space habitats. So that's where I think the future is going to go. In terms of the mass that's available, this is the big like aha that I had a couple of years ago, and I think most people that have studied this have stumbled upon it, but this might be new for a lot of you. The mass resources of the solar system are incredibly large, although not unlimited. But let me give you a sense of how large they are. If we could build those free space habitats using material, rocks, metal, other materials, gases, etc., from the resources available in the asteroid belt, okay, we would produce roughly an area of 500 times larger than what's available on Earth today. 2 times 10 to the 17th meters, which I know is a mind-boggling large number, but it's roughly 500 times larger than what is available on Earth. That's from the asteroid belt alone. Now, that's not all the resources in the solar system. If you now consider the mass of all the moons, not just our moon, but the moons of Jupiter and the moons of Mars and the moons in the outer planets, now we've got a gargantuan amount that's more than 100 and I think 300 times larger than that. And so now we're talking many tens of thousands of times Earth's surface area. And if you add up the mass of all of the stuff that isn't the sun in the solar system, not saying that we should dismantle the planets, but if we could in some far future date utilize all that material, you would have a vast amount depicted by this basically straight line on the bottom, which is the edges of an enormously large circle, which shows just how much surface area would be required. It's about 1 billion times the surface area of Earth. Would we ever need that much? Probably not. But it basically shows that there's plenty of mass available to build lots and lots of space for a larger future population. Okay, so we'll return to this question in a little bit. Another constraint, however, so that doesn't sound like a constraint, but it actually is. We can't do more than that. So that is a mass constraint, fundamental to the solar system. Now, the other constraint is that you can't just build something once and have it last forever. Everything breaks down eventually. The Earth is a harsh environment. It's harsh enough on Earth. This picture here gives you an idea, rusty boats. And so even if we could recycle and sort of rebuild stuff in space when they wear out, you would still have losses inevitably from stuff that breaks off and floats off into space, things that are just too worn out to really use, accidents, mistakes, deliberate sabotage. All of that stuff is going to lose material into the interstellar medium, and we're going to have to mine more of it. And so my best estimate is that if you could have a really robust recycling economy, maybe you could stretch out the life of a material, rebuilding it time and again out to a few thousand years. So I put 10,000 as an optimistic estimate, but that still is less than infinity. And so that means that now you're going to have to, further limit how much stuff you can build because you got to replace it eventually. So material lifetimes matter. Another huge one is propellants. The mainstay of how we move around in the solar system is using propellants, which are essentially hot gases that get shot out the back of a rocket and push the rocket forward. Well, that really works well for getting to high speeds. The problem is there's a lot more mass that gets shot out the back of the rocket than what moves forward. And this is known as the tyranny of the rocket equation. And it's the one math equation I have in my talk here. It's basically an exponential relationship between speed and how much mass you need. And to simplify, because I'm not going to walk through all this, if a rocket can achieve a final velocity that's twice the speed of the exhaust that's coming out the back, it has what's called a gear ratio of about 7, and that means that you need 7 times the mass total as what you end up propelling forward. And so the mass of the propellant is roughly 6 times what you accelerate with the rocket. And this is for every time you take a journey. So if you have a rocket that gets reused many times to move people around different parts of the solar system, you can easily see getting to like 100 times or more the amount of matter that you're moving around is kind of consumed in one go with propellants. And so propellant is also going to be a way to limit how much material and ultimately how much land we can build with solar system resources. Propellant use will dominate and therefore should be minimized as much as possible. So then the question is, how long do we plan to be around? Well, The Egyptians built the pyramids several thousand years ago. Human history goes back quite a bit before that. In terms of pre-recorded history, we have evidence that modern humans were living, as early as now, around 300,000 years, at least anatomically modern humans. They didn't have the same culture we have. But on the other hand, the dinosaurs lived for 100 million years in different forms. And so the longevity of a species on this planet could be very long. How long could we live within the solar system? We shouldn't just assume we're going to be around for a couple hundred more years. It's such a pessimistic view. But how long? We don't really know, but it could be a very, very long time. And so we should be planning on long-term living and not just, oh, well, it'll get us the next 1,000 years and we don't have to worry about it out of that. We should really plan to stick around as long as possible. So I won't answer the question of lifetime, but just think millions, not hundreds or thousands of years. What would ultimately limit our civilization? Well, I could think of 3 astrophysical phenomena that could really spell disaster if we stayed on Earth, but they're actually survivable with space civilizations, space settlements. One is a nearby supernova that happens every 100 million years or so, and it would essentially strip the ozone layer of its protection and make life very difficult for life on the surface for a period of time, probably several years. It could extinguish a lot of large mammals on this planet. But in space, we will be largely protected from such a thing because we won't have an ozone layer to get stripped. We can build these thick shielding layers. And so I don't think that it's going to be a problem. A bigger problem is the brightening of the sun. The sun is slowly increasing in its brightness, and it increases about 1% every 100 million years every time there's a supernova. Over 1 billion years, it will be roughly 10% brighter, and scientists think that that will be enough to essentially boil the atmosphere away and dry up our oceans. And so Earth will be a pretty inhospitable place 1 billion years from now. But even that is survivable in space because a brightening sun just means we have more energy, we can build more habitats. It doesn't spell doom for the climate within those civilizations. So, and then finally, what happens when the sun becomes the red giant and envelops the inner planets? Well, yeah, that spells game over for the inner planets, but you can build these space habitats in the outer solar system and easily survive that. And now you have a much larger energy source to run your economy. So that's also survivable in outer space. These are not game-changing events necessarily. So then that brings us to the question of energy. Where are we going to get our energy from and how much do we need? The sun provides an enormous amount of power. 10 to the 26 watts, which is such an enormous number. I wanted to put it into some perspective here that if we captured even a small fraction of the sun's output, and I put 2.5% here for some reasons I'll get into at the end, but we could capture that small fraction of the sun's output, convert it to electricity. We're looking at some unfathomably large amount of power, which is 50 million times more than the Earth receives and 500 billion times what humans currently use. It is a staggeringly large amount of energy. It feels like it would be almost certainly enough no matter what we do going forward in the future. But I ask the question, is it? Because in fact, forecasting what humans might use in terms of energy going forward, we come up with some surprising conclusions. So let's go through a very quick power budget here. I'll be fast. I know there's a lot of numbers and words here, but I won't read everything. Humans currently consume about 3 terawatts, or 3 times 10 to the 12th watts. It's a trillion watts of electricity. That's about 300 watts a person, 300 watt light bulbs. That's worldwide. In the US, we consume quite a bit more. It's more like 10,000 watts a person. We might use more as an industrial spacefaring civilization, more lights, more appliances, more, stuff, but probably agriculture is going to dominate, as we were talking about earlier. And so, providing the light to grow our crops is going to by far dominate our energy needs. And I estimate, including the light needed for ecosystems, it's more like 5 megawatts a person. So now we're in the millions of watts. But making all those propellants that we talked about a few minutes ago so that people can move around the solar system is actually going to cost quite a few times more than that. I peg that conservatively at 20 megawatts a person. So now we're up to 25 total. But surprisingly, The biggest use of energy in the future might be data. We do not consume very much power on the whole from our data centers and our electronic gadgets today, but that use is growing very quickly. And within 70 years, it could exceed a gigawatt per person at current growth rates. There's no telling where that's going to end up. So I predict that actually it will be the use of data technology that will dominate our future energy budget. But that's not it. Using propellants to move around the solar system at fairly modest speeds is one way to conduct a future civilization, but it's very resource intensive, and it doesn't actually move things very fast when you're talking about interplanetary distances. So one way that people have been exploring for moving much faster is something called laser sails. And these are currently being explored as ways of getting to nearby solar systems like Alpha Centauri system for exploration and getting there very fast. We believe that we can get over 20% of the speed of light using a very powerful laser beam to illuminate a sail, such as is shown here, and accelerating a lightweight spacecraft to these incredibly high velocities. We don't even need to travel that fast within the solar system to make a big difference. I estimate that if we could travel at 1% the speed of light, which is 3,000 kilometers per second, this would allow people to travel from Earth to, say, Saturn, which is roughly 10 astronomical units away, in 10 days. And each person takes one of these trips annually. This would allow the entire solar system to be connected. It's equivalent to traveling overseas. Obviously, we don't take 10 days to go overseas, but back in the sailing ship days, we did that. And people could also travel more slowly to more nearby locations. It would still be a lot faster than using rockets. But to have this capability available would now require on the order of 5 terawatts or 5 trillion watts per person, which would dwarf all other power needs by a large margin. So I will quickly show you what 5 terawatts a person looks like, and then we'll get into kind of the final conclusions and discussion. So how much is 5 terawatts? Well, 5 terawatts is 5,000 large nuclear power plants, or 20,000 kilometers of Earth-based solar panels, which is about the size of Massachusetts. This is 2 times our current global electricity use by everybody, but this would now be a per person energy need. So it is an enormous increase from today. It's billions of times what we currently use to power a future civilization. Does this sound impossible? Maybe, but as I think I demonstrated, there is plenty of energy out there if we capture the energy of the sun and convert it to electricity and other forms of energy. And so the question then remains, what's not to like with that picture? We've got plenty of energy, we've got plenty of room, we can travel as fast as we like, we can have fabulous internet connections and virtual reality. Each person can live in their own estate, in orbit, Earth gravity. What could possibly go wrong with this picture? I'm going to give people a minute to think about it. Maybe I'll actually pause and ask, anybody want to venture a guess for what might happen if we go down this pathway?
One thing I would suggest is that very large space settlements could be hit by impactors that would destroy them and kill as many people were on board at once.
Yeah, that's a good one. I'll address that in a moment. But thank you for that thought, Nick. Anybody else?
I think there might be political considerations that we're not talking about yet, that governance and things like that. I was going to say space junk, but that was already taken. But yeah, like the political, the economic. If you've ever watched The Expanse, you can see kind of a fictional version of how that would play out. So.
Oh yeah. No, it definitely concerns me. Yes. What if a small number of people control all these resources? That's right. Yeah. Any other thoughts before I proceed? We'll have a chance at the end to discuss, but go ahead, please.
I sent something to you, but I'm not sure if that makes sense. So I'll just leave that to you if it's a good point or not. Otherwise, it's fine.
Oh, did you have something else to contribute now? Sorry. Or are we going to wait?
I was just wondering, since it's getting closer to speed of light, then still traveling large distances, even though you accounted for that with the speeds, I guess. I was just wondering about time dilation and things like that.
Oh, actually, I can address that right away because that's an easy one. You only get into things like time dilation and so on at very close to the speed of light, above 90%. The effects are just really not that big at lower speeds. So certainly at 1% the speed of light, it's a non-issue. It's really no different than just traveling in a rocket.
Jeff has his hand up.
Oh, I'm not seeing everybody. Go ahead, Nick. You can call on one or more per person, and then I'll proceed.
Go ahead,
Okay.
Jeff.
Yeah. One of the things about long distance travel, for one thing, a good thing about it is that once people are used to living in the stations, a generation ship to another star is just basically lack of scenery for a while. Because if you've had 3 generations living in a space station, having 5 or 6 going to another star, assuming they have enough resources to get there. But one of the things that I was think is what's not to like is who's going to build it? How will they get their investment back for building it? Because that's what people, that's what motivates most people.
Yeah, I have obviously not touched on the economics and will not, because I can say that it's quite costly today. It's almost unimaginably expensive to do something like this, but I will save some good news for the end about a pathway to that. So, okay, well, let me go on. And actually, it's kind of interesting, Jeff, that you sort of thinking already about migrating to other systems. I wasn't going to go there, but there is sort of a little implication in my answer to what's not to like. So let's see if you can spot that. So what's not to like is population growth. Okay. I don't know how many people here have read or have heard of this book, The Population Bomb. It was a 1968 blockbuster piece of analysis, which was basically warning that our flagrant use of resources was going to cause a big environmental problem. The person, Paul Ehrlich, was not wrong in principle that an expanding population will use more and more resources. Where he got it wrong is that he didn't realize how quickly we were becoming more efficient. But what happens as we use all of these resources and continue to expand as a species is that eventually we reach a point, which I estimate is around a few trillion people. I'll call it 1 trillion for now, where we're now consuming all of the resources of our star, and we don't have anywhere else to get our energy. And so if we haven't gotten a handle on our population by then, we become, basically we face, as I wrote here, a population crisis like no other in history, where there is no other place to turn other perhaps than to other star systems. And if for anybody who thinks, oh, well, that's so far in the future, don't worry about it. If we continue growing at our current rate, which is about 1% per year, and admittedly that rate itself is decreasing and has been over the last couple of decades, but if we were to sort of stabilize at 1% per year, we'd get to that point in 500 years. 500 years is tomorrow when it comes to a human civilization. We would barely be getting started in terms of building our solar system-wide civilization when we would reach this resource limit and be completely unprepared for how to deal with it. At slower rates, it could take a lot longer. And I think that would probably be the way to go, is grow more slowly and you have more time to prepare. But there's still the problem of, if you're continuing to grow, you're going to reach a point where you can't support the population with the resources that you have, even in the entire solar system. And so the natural question people ask is, well, okay, but maybe there is more energy out there. And so I looked at this a bit, and the answer is, well, there's a little bit more. There's actually enough fusion fuel in terms of deuterium and helium-3 in the outer planets, particularly Jupiter, but also the other large planets, that could provide actually quite a bit of fusion-based energy. We can get fusion to work, you can mine it. Forget about the fact that you're dipping into the planet's atmosphere and eventually stripping it of all of this gas. But you could, if you add it all up and you figure out how to do it, you could get an additional 3,000 years worth of the sun's energy by fusing all of that resource. But the problem is that if you're still growing as a population, 1% per year means you actually only have another 340 years worth of energy resource before you've used that all up. And everything else that I've been able to find in the solar system are vastly smaller than that. And so in short, without population control, exploiting the outer solar system resources might let you get to a quadrillion people in 1200 years, but then you are really out of options and you have nowhere to go other than other solar systems. And so the conclusion here is that, I have separately figured out how much mass a person needs. Every person would need to sustain themselves in space. And it's about 500,000 kilograms per year per person, which is a huge amount. But, even times 1 trillion people, given the resources of the solar system, that's a very small amount of matter. We'd be using all the energy of our star, but we'd only be consuming about 0.02% of the asteroid belt mass every year. And it would be essentially a way to sustain ourselves for billions of years, far, far, far longer than the sun will even be able to stay lit. So we got plenty of mass resources if we stabilize at 1 trillion people. If we grow to a quadrillion people, we'll be consuming 1,000 times more every year, but still we wind up only consuming a few millionths of the solar system resources. And so what I'm just trying to drive home here is that it is energy and not mass that is ultimately going to limit us as a civilization. And so that's the part of the puzzle that we really need to get our hands around, and in particular, limiting our population to a very low level or essentially zero growth is eventually going to be necessary unless we expand beyond the solar system, which maybe we will one day. But the good news is that despite these sort of warnings, there is plenty of material and energy out there over the next several hundred years for us to expand into the trillions and have a very vibrant, expansive civilization. We just need to keep population growth firmly in the back of our mind and not let that creep up and surprise us. So that's the end of this part of the talk, but actually I want to have a little bit of a preview of why I'm involved at this company, Orbital Assembly, and how it's helping to advance this vision in our own small way. And so I'm just gonna, if you can just entertain me for 5 more minutes, I'm gonna give you a quick rundown on what we're doing, and then we'll have Q&A. So what are we doing to move us closer to a spacefaring civilization? I'd like to introduce you to Pioneer Station, which is the first station that we're planning to build and operate in low Earth orbit, which will have artificial gravity. We're planning to get this in operation as soon as 2025, assuming full funding, which we're on path to receive. It would have an occupancy of some tens of people, up to 54 in an expanded configuration, not the one shown here, but something slightly larger. We have the ability to spin it at various gravity levels up to about half a G, half of Earth's. And so we could easily reproduce the gravity on the moon or Mars. And a lot of this would be experiments to find out what level of gravity people are going to really need in order to survive and thrive. It'll certainly be better than microgravity. We can build this quickly. We think that we can get going in roughly 3 years' time, 3 to 4 years' time. And we plan to provide a hybrid gravity environment where you can both have microgravity as well as partial artificial gravity. So you can walk around the station, sleep on a regular bed, use a bathroom normally, carry your cup of tea or coffee, your laptop stays on your desk, and yet you can operate in microgravity when needed. And so you kind of have the best of both worlds in space. It will greatly alleviate space sickness and make it a lot easier for people to live longer in orbit. We think that this is going to be a winning combination for space manufacturing and space exploration. So we're very excited about this concept, which we're starting to get a lot of people interested in. Our vision is that we build the first part of the space station as soon as 2025, which would be a microgravity facility. And then with additional funding, we would build the full rotating version a year or two later. We are on a path to being able to build 3 full stations by the end of this decade. And the capacity would increase beyond that, where we could build these stations, not just around Earth, but also around the moon or elsewhere in, as it's called, cislunar space, Mars, et cetera. And this isn't the only thing that we're going to build. We eventually plan to build much larger stations that have capacity of several hundred people at a time and a much larger interior volume. This one, which we've been calling Voyager Station, rotates at a constant rate. So instead of variable gravity, we have constant lunar gravity in this case, and it would create a very stable situation for people to operate. We envision these stations in different locations around the solar system eventually. And this is really the stepping stone to that vision of having enclosed pressurized habitats with Earth level gravities in them and larger interior volumes to support plants and sort of an open air experience. But this would be the next step along the way into that final vision. We have a lot of strategic partners that we're building up relationships with, and we're very excited about the progress and interest that we've had from throughout the space industry and beyond. So we believe the future is in rotation, and we're trying to build a path to get there. We welcome your participation in this journey, and I will leave you all with this question for discussion. Can you embrace this vision that I've projected? Some people have already given me some comments. What's appealing? What's not appealing? How could the vision be improved? I look forward to the discussion to follow. So I will cede the floor to the other participants.
Thank you, Jeff. And we already have several questions in the chat. Mark Wagner has asked, what vehicle will be used to get pieces to orbit, and how do visitors get back and forth?
Okay, so if we're talking about the stations that our company is planning to build, can you clarify that question?
That was my understanding, but if Mark is still here.
Yeah, for sure. The stations you guys are planning to build, I was wondering both how you planning to get the pieces up there and how you would plan to get visitors up there.
Yeah, so Pioneer Station is built to be assembled in a small number of rocket launches. So it would not all be done in one launch, but it would be done using existing space architecture. So for instance, we don't rely on Starship as a lifting vehicle. Of course, we and everyone else would love to take advantage of the larger capacity and lower cost when that is available, but that is not what we need in order to be successful. Yeah, I mean, we're going to use whatever is available in the market as soon as it's available. So for now, we would be getting people up and down using, Dragon capsules, or you can see in this image that I have in my background here, a number of Sierra Space Dream Chasers. Those would be largely used as kind of lifeboats in case of an evacuation is needed, but they can also be used to transport people to and from the station as well. Although in this configuration, you can't dock on the outer ring when it's rotating. You have to dock in the center. So for Pioneer Station that doesn't have that capability, the rotation would stop. You would have the docking spacecraft, whether it's Orion or Dragon or Starship one day, or the Dream Chaser, to connect, and then the rotation would start again. But yeah, that's how we plan to bring people and equipment up and down.
So that actually leads to another question, if I can follow it up real quick. But that last slide you had of the people standing in the stateroom with the panoramic view of the Earth. I've seen studies on like how much or how little gravity is sustainable, and how much the Coriolis force for spinning, how disorienting that is to people, how much it can sustain. But I haven't given much thought yet to the fact that won't be the view looking out the window. Like the Earth is going to do this, right? Like, has there been any sort of studies on how disorienting that will be for people? We even heard from some folks who've done the short parabolic flights, not parabolic flights, the suborbital flights.
Yeah,
that it's I think it maybe was Chris Bosshausen when I talked to him before, that he purposely oriented himself upside down, and it was too disorienting. Like his brain couldn't make sense of space and the Earth until he set himself back with the Earth. And if the Earth is doing this the whole time, what's that going to do to people who are just visitors? Right?
Well, let me try to answer that. So first of all, we do not know the answer to that. Is the quick question. The quick answer, I mean. There has been very little work done in space in rotating environments. Really, there has been just a couple of trials where, we've done a tether experiment several decades ago where you basically have, two ends of the spacecraft, they're rotating around. That was not spinning fast enough to produce appreciable levels of gravity. The space shuttle had done a couple of rolling maneuvers, again, very, very small, so almost undetectable for a human. The only experiments we've done at appreciable gravity levels in space have been at a very short arm centrifuge and on non-humans, like rodents, for instance. And so basically there is a big gap between what we think might happen and how people will respond and what we've actually verified. Most 99.9% of the research on artificial gravity has been done on Earth, where we have to find a way of kind of offsetting the Earth's gravity that's always present. And so the results really aren't completely valid, even though people have done some very clever things. And of course, you can go up in a suborbital flight and get like 2 minutes of microgravity or partial gravity if you accelerate the spacecraft. The parabolic flights are probably the best way. You can get about 30 or 40 seconds of, say, lunar gravity if you do a particular kind of flight. But that's not the same as having somebody live there for days or weeks. So the answer is—
And they don't have windows. As a general rule, you're not looking out at the Earth. Like they're not even experiencing this, never mind.
Well, if you're, I mean, I'm talking about the physiological effects of rotation, and does that alleviate these symptoms? We're almost certainly sure that it will help, but we don't know in detail what will work better and what might be a different problem. As far as the disorientation of a spinning scene, all I can say is we don't know whether that's going to upset people. I guess you could do experiments on Earth where you just have a rotating, image, and you sort of see if people feel seasick. But the nice thing about virtual reality is you could produce a static scene of outside through a high resolution monitor, even though the space station itself is spinning, and it's still a real view out the window. It's just not the actual, photons. So there are easy ways to correct for this, but from everything we've been able to tell, people like actually looking out the window and seeing the real Earth, even if it is spinning. I think people will like to look down and see what's going on.
I wonder if it'll be more appealing for people to travel to the hub to look outside.
It could be that they'll want to do it, in the center, and it is disorienting. So these are, this is a big experiment. We're excited to see. We hope there will be people who will volunteer to subject their bodies to possibly unpleasant effects of like high spin rates and so on. But the only way to find out is to do it. So we're excited. Rob, you're raising your hand. Go ahead, unless somebody else was in the queue.
I was just saying I volunteer as tribute. Just on me.
You volunteer. Please. Yeah, we're hoping most people will volunteer their experiences. It's still an opt-in kind of thing, but anyway. Any other questions?
We have a question in the chat from D, who asks, I assume, once again, like Mark, asking about your last plan outline. Who will live there and how much will it cost them?
Well, currently, we're not planning on having people live there. They are for visitation. I mean, we will certainly entertain the idea of selling somebody a module or part of a module if they wanted to, but it's not a huge amount of space for actually living. I think that's kind of a next generation beyond Voyager. I will say in terms of cost right now, and this is about, because we're not building this Voyager station that's rotating in the background yet. The first station that we have in development is Pioneer Station, that should be up by the middle of this decade. And you will find, I'm not going to quote prices over the webinar here, but you will find the prices quite attractive by contemporary standards. But we have to charge market rates. There is a lot of technical investment, and we can't control the cost of getting to orbit, which is actually the majority of the cost of getting to our station right now. But we hope that will be falling rapidly, with the advent of reusable rockets that are coming.
Nadia, please go ahead with your question.
Hi, I was just wondering, so is it basically like a hotel in space? Well,
yeah, it's a hotel plus other things too, research, manufacturing, but yeah, you can call it a hotel in space if you want.
Okay.
Did you have a question about that, or just is it a hotel or not?
Yeah, that was pretty much my question. Because there's been rumors of hotels in space coming out, but obviously there's different kinds of habitats and things like that.
Yeah, I mean, we will definitely be offering hotel-like rooms. We don't know what the market is going to bear in terms of space, space tourism. We hope that being on a rotating station with more room will be attractive to people and it will exceed all expectations, but it is being designed as a multi-use facility. Rather than hotel rooms, it might just be bunks for people who are doing experiments to stay, with a few tourists mixed in there. But time will tell as we develop these offerings and people share their experience of what it was like. So
That's really interesting to hear as well, in a way, because often people believe that space is just for people in STEM, especially engineering. But obviously, if you bring in tourism and overnight stays, that's bringing in the hospitality industry, which is probably something people really didn't think could be an option to them. So it's
That's
quite
right.
nice to hear. Yeah, I don't have
We're
much else to
definitely-
add.
yeah, we're definitely interested in supporting space vacations as a destination. So yeah, that's coming.
So
Thank you.
Anyone? Yeah, Rob, and I know there's a few in chat too that maybe Nick,
Oh,
you can
okay.
read next, but go ahead.
Oh, I was just going to ask, I had asked earlier in chat, how long do you think it'll take, I guess, for genetic adaptation, or I guess microevolution, to kind of take over, so that like humans in like less than 1G environments will be able to kind of be normalized? What do you think that's the prospect on that?
I'm not a bio physicist or whatever you would call it. So genetic, yeah. So I really have no idea. I have interviewed a few people who think more about these things. I run a podcast called Our Future in Space. I welcome you to check it out. We have a lot of interesting guests on, including Nick Nielsen, who is our co-host here, and a few other folks who organize this conference. But yeah, I mean, the short answer is I have no idea. It's my personal belief that while there might be some adaptation, I don't think we're going to adapt to MicroG. I think that we may find that it won't be too bad to sustain ourselves in a less than 1G environment, but we might find that we really need the full Earth gravity, occasionally. Maybe you need a dose of it every month or, or longer. We might find that living at Mars gravity is just fine for fully formed human adults, but children need more. We just don't know. And it's going to be very interesting to see once we have a facility on orbit to actually test these things at scale. Right now, we just don't have that possibility. Other questions, particularly about the first part of the talk. I'm glad people are excited about our business plans, and I'm happy to talk about that too. But anything from the earlier half?
Earlier in the chat, there was a question from Dirk Razor, who asked, what is your personal realistic thought about the near future timeline, commercial space stations, colonies in the moon, Mars, etc.? And what is the estimate of when the need for commercial/private astronauts will dramatically increase?
Well, I've been in the future prediction business a long time, and I can say it is really hard to predict the future. What I have tried to do and what I presented to you was essentially I was using bounding cases. If you notice, I wasn't really saying when, but I was saying what or how much is possible. And the few, year figures that I included were essentially a statement of, at a particular rate of growth, how long would it take to reach this level or this point. So what I can say, this is speaking more as a space entrepreneur, there is a pent-up desire to have, to have more possibilities in Earth orbit for doing experiments, testing, as well as tourism. And, there's something like on the order of 8 to 10 space stations on the drawing board now that will probably be built and operated by the early 2030s, right? I mean, you're looking at, including ours, there's like 5 commercial stations planned. We'd like to build more than one. I'm sure the other competitors would also like to build more than one eventually. We've got the Lunar Gateway. We've got the Chinese station that's already up there. Both Russia and India want to build their own stations, and there might be another couple who eventually will have that capability. So, we're kind of going from 1 to 10, or 2 to 10 if you count the Chinese station that's already there. And that's just in the next decade. So, United Launch Alliance put out a white paper a few years ago called Cislunar 1000, which was a vision. They were not specific about the date, but they were basically saying within a couple of decades, we would have 1,000 people living and working somewhere within the Earth-Moon vicinity, including the lunar surface. I think that the possibility of having a lunar base that's kind of similar to, say, Antarctic Station, plus a number of stations like this one in Earth orbit and a little bit beyond, say by the 2040s, is very possible with continued funding, and we don't like crash our economy or have a world war. These things could easily take place. There's a lot of economic benefit from it. And the costs are going to be dropping precipitously with things like reusable launch coming online fairly soon. So I'm fairly optimistic about it. Of course, I have to be because I'm in the space business. I want this to happen. So take that with a grain of salt. But in terms of the larger term vision of building these enclosed space habitats, I think I can say with confidence that's definitely a second half of the 21st century proposition, but it's not like hundreds of years from now. There's no reason in principle why you can't build what I'm showing behind me, but just larger, and have a real, living situation where people can retire there or raise families there. I'm bullish on that vision, but there's a few steps we got to take first before we get there.
Do we have other questions? If no one else has a question, I will elaborate on some of the themes that you brought up earlier, which I found really interesting.
Sure.
One thing you brought up that I'd never thought about before was the question of material strength and its loss over time and the need to rebuild these. So do you see this as being a matter of you build a big settlement in space and then you have to periodically refit it like a ship? Or is it something you're continually redoing, or do you have to abandon it, melt it all down, and start over again?
Oh, okay. Yeah, no, I'm glad you outlined all those possibilities. I see it as being something that you would probably, for certain parts of it, you would just sort of patch it as you went. You get a meteor strike and part of the shielding comes off. You put some new stuff on, right? Or you realize that something is getting weak, but it's only in a few places, and you go and internally or externally, you refit that, and it's kind of good as new. In some cases, you might have to abandon the station for a while in order to do a more major retrofit. But honestly, I don't think anybody has really looked into the details of how you would maintain these multi-kilometer scale structures. They're bigger than any bridge or skyscraper on Earth. I mean, maybe not any bridge, because there are some that are several miles long, but it's done in a very different context. Bridges are never dismantled and rebuilt, or it's to be avoided, right? You don't want to do that. You want to keep it going, and so it's essentially you replace things that wear out, but you design it so that it be continually updated. And I think that is the better way to go. Especially if you're talking about longevity, and these are people's homes and lives, and you've got ecosystems that might take decades or even centuries to mature, you don't want to have to abandon it, suck all the air out of it, kill everything, and then start over again. So yeah, I would say that these should be continually habitable and retrofittable as you go as the ultimate goal. But we just haven't done the studies, and we honestly don't even have the real world experience to be very informed about what that would look like yet. But it's exciting to think about.
We have two hands up again from Rob Watson and then Motoshan.
Can I suggest that Motoshan go? Because Rob, you've had a chance to ask a couple questions. Okay, thank you. Motoshan, go ahead.
Yeah, thank you so much.
Sure.
So my question is, there's so much exciting stuff going forward in the future of for space industry, but a problem that I see is students do not have enough skill sets developed in their at this present moment to go into the future. There's this big gap of talent acquisition and skill set training which students really need to do. So how do you propose we should train students for the future endeavors that are in the space industry?
Well, I mean, so one, I would say there are, I would say, there's kind of a renaissance going on in terms of aerospace engineering. There are specifically with regard to those that are focused on preparing students for the commercial space industry. And I'm aware of several US universities that are doing that. I'm sure there are several more around the world that are also investing in that. I would also say that, you know, as the space industry grows, there are a lot of on-the-job internship opportunities that will be growing. We certainly hope to hire a bunch of interns in the near future. That's another way to learn the skills that you need. And you don't even need necessarily an advanced degree in order to make a contribution. There's a lot of student activities where now, for instance, we have a partnership with Arizona State University, and undergraduates are doing real engineering problem solving, you know, with companies like ours, where they're taking the problem, breaking it down, doing modeling, and coming up with very, you know, useful outcomes that are not unlike what it would be like to work at a company such as ours. So I would say that there are increasing opportunities. You know, I don't know if you're specifically speaking about you know, your personal experience, but not finding enough options or opportunities. But I would say that overall, there is growing interest, although yes, we're kind of behind at having enough STEM programs to satisfy the demand. But also it's about more than STEM. You know, we need sales and marketing people. We need, you know, we need architects, we need human factors people. We need people who are going to think about how to manage a closed group of people who are isolated for a while and might have social dynamics issues, you know, so psychologists and sociologists are going to be important as well. So kind of the whole range. But if you wanted to follow up, if you want to ask a follow-up question, please.
I was explicitly talking of like the whole global population. Like so much of the world is behind, and there's like a big gap between even developed countries and like developing countries, which we can see. And I'm personally from a developing country, Pakistan, and there's like, to be honest, there's no space program. There's literally 0%. No, I can't say 0%. There's like a 10% community which knows about space science and stuff. So yeah, that's what I was thinking.
I hear you. It must be very frustrating if you're living in a country that has no space program and sort of no foreseeable way of getting into it other than going to another place. I mean, were you on the astronaut panel this morning where, you know, the Korean astronaut was talking about her experience and having like very limited options when she was going through? I think that is starting to change, and there are more countries that in the past had never had a space program and are now starting to develop them. And they're definitely several decades behind, but I believe that they will get there, particularly as space becomes more affordable. There's a democratization of access to space technology. So I would say be patient. I mean, obviously don't wait around, you know, be proactive, but there is a lot of there are a lot more options for smaller developing countries to get into this game than there ever has been before. So, all right, any other questions? I guess we're about over.
We have run out our hour. So
Yes.
thank you, Jeff Greenblatt, and thank you for everyone who came and talked and asked questions.
Yeah, thanks for your participation. It was a good discussion.
So I'm
All
going to
right.
turn off the recorder now, and we'll have 15 minutes break until we come back.